Okay, 6.3. We have done Laplace transform, and all the previous two sections we focused on the first order differential equation. Now we want to move to second order differential equation, and once we have done that, you will be able to see actually we can do this for any higher order as long as it's linear. Okay, so let's think about the second order differential equation. The most important example we had before was the harmonic oscillator. Okay, we have the friction, we have the spring mass constant. Let's start from the easiest one and try to see, can we use Laplace transform to help us to solve this problem? Okay, now I want to actually start from the very basic one instead of the PQ one. Remember, okay, this is where we have the mass, we have the spring constant, and then we clean everything. We have this. So after that, our solution is going to be sine and the cosine, and any possible linear combinations, of course. But the two basic solutions we have, the basis, are going to be sine, cosine. So the first thing I want to point out is this number here is called the natural frequency of the spring. Let's call it omega. Okay, then I can rewrite this one here to be. So there's nothing difficult. It's just I replace the k over m by another constant because this one has some physical meaning, and this makes the whole thing looks a little bit nicer. All right, so we will first do this. After we have done that, we are going to add the damped, underdamped, overdamped, and the underdamped, the overdamped, and the critical damped in, so the general case. After that, we will deal with some cases we have never done before. That is, we do have y prime prime plus omega square y, but then we are going to start to have external. Okay, force coming from maybe an electrical field or things like that. So we are going to have external force. This is something we cannot handle before, because everything we had before, we have y prime equals a y, but we only have the homogeneous case. We do not have anything with a plus a b vector. Everything here is always 0. So everything we have done so far, we can only handle his homogeneous case when this one is 0. But now finally with Laplace transform, we can start to add in external forces. Okay, so from here you can see Laplace transform can handle everything we have before, and also we can handle something that we cannot handle before. So that's the key. Of course, we start with the very simple one and try to see how we solve this with Laplace transform. So how do we do that? Well, the first thing we want to do is we want to actually do L on both sides. By linear property, we can take the constant omega out. Ly, this one is already clean. The one which is not clean is going to be this. Well, what do we know? We know Ly prime minus y0. Okay, that's the property we know about Laplace transform. We never had a property of a second derivative. But now if you think about it, okay, how do we do the second derivative? We can view the second derivative as a first derivative. It's not the first derivative of y, it's the first derivative of y prime, and then another prime. Therefore, we can treat y prime as a new function. Then what we have here should be y0, where y is the function here. So actually, we need to have y prime 0. So this is certainly something we can do if we treat y prime as a function. Then after that, what we can do is, now we can do Laplace transform again. This time, we're going to do the standard one. From here, you can see adding more derivatives is no problem, because the third derivative will be a first derivative of the second derivative. So at least you can do things at the second derivative level. So every time you apply this one, you can reduce the order of derivatives from the first order to no derivative, or from the second order to the first order, or third order to the second order. Okay, and then you can just take the second order part, do it again, and then take the first order part, do it again, and eventually everybody will be in terms of Ly. So Laplace transform, not only it can handle the first derivative, actually if you just keep doing Laplace transform, you can handle all possible derivatives. That is good. What is not good? What is not good is every time you apply the Laplace transform for the derivative property, you are going to generate a value at 0. So the first time you do it, you are going to generate a value of the function which you viewed as a function which is y prime. And then you are going to generate another value which is y0 the second time you apply the Laplace transform. So you need these two numbers. But here's the beauty. The beauty is if you have a second order derivative, a differential equation, to solve the initial value problem, you do need two initial values. So actually, in general, these two things are known. From here, you can see, okay, Laplace transform is an ideal choice for solving initial value problems. Because if you have second order derivative, you do Laplace transform for twice, you need two initial conditions. But to finish, to have a well-posed initial value problem, you do get offered the two values you need. So again, focus on initial value problems. So this is good. With that in mind, now what we can do is we can take y prime prime plus omega square y equals 0. Now what we are going to have is s L y prime minus y prime 0 plus omega square Ly equals L0, which is just 0 because you're doing integrating from 0 to infinity 0 dt, right? Okay, so of course that's 0. And then what we can do is we can do it again. Let me see it. Let me take this part and expand it. Now, what do we have? We have a lot of numbers, and we do have a lot of Ly. We just need to put all the Ly together. Somehow something is wrong. What did I do here? Oh, I'm only doing the undamped. All right. Okay. Minus sy0 minus sy prime 0 plus omega square Ly equals 0. Therefore, we have Ly equals sy0 plus s. Somehow this is not right. What did I do? What I did is here. This parenthesis should not be here. That's why. There's no s here. Now it's more like it. Y prime 0 plus sy0 divided by s squared plus omega squared. Okay. Now to finish this, all we need to do is we just need to write down y equals L inverse, whatever we have here. Okay, so the problem is how do we find the inverse transform of this? Otherwise, this one can be solved. Okay, so that's what we have so far. Good. So in order to finish this, we need to be able to find inverse Laplace transform. But what is the inverse Laplace transform? Well, technically we know how to solve this, right? We know the answer is going to be sine and cosine. So I'm guessing, and it's not a unreasonable guess, that is this one, if you do the inverse transform, it's gonna be sine omega t or cosine omega t, or maybe some combination of them, because I do know that the solution is something like this. So the first job, probably what we want to do is we want to know the Laplace transform. Of sine cosine. Let's put an omega here. Okay, because it can be either frequency, and you can even have like 3 sine omega t, but by linear property, it's pretty important. It's pretty easy to just do sine omega t and times 3. So the most variation you can get from here is going to be sine omega t and cosine omega t. Okay, we want to know the Laplace transform of it. Okay, how do we do it? Let's do sine. Now this reduced to something we have done before in calculus 2. That is when you have something like a sine x e to the x. Okay, I don't want to do it in this way. It's doable. Okay, but you need to do integration by parts for twice. If you try to recall, this is some pain in the butt exercise we had in calculus 2. That is, we have to do integration by parts for twice. And then eventually we'll end up solving the value from an equation, because we're going to see this term again for twice. Okay, and then we finally end up solving it from the equation. So that's how we're going to do it in calculus 2, but it's going to take a big chunk of time. So we can leave it as an exercise. Try it. And you should get the same answer as what we get from the method I'm going to introduce, which is a little bit easier. Okay. So alternatively, how do we do this? Okay. This is what we're going to do. Okay. We take y equals sine omega t. Now we do know this one satisfies y prime prime equals zero, of course, but this is not the only thing that satisfies this. However, I can somehow give you some special initial points. For example, I can tell you y 0 equals 0, because if I plug in 0, I got 0. Okay. I can also tell you y prime 0 is going to be, well, what's the y prime of this? It's going to be omega cosine omega t. It's going to be omega. So if I tell you this, the solution is going to be y equals sine omega t, firm. Why? Because we have initial value problem, so we don't have C1, we don't have C2, we don't have cosine omega t, since we already give you all the initial value you needed, so your answer is unique. Okay. So somehow we know this function satisfies this. Therefore, this function, if you take the Laplace transform, should satisfy this. Okay. Now let's do it. It's going to be S L y prime minus y prime 0, but we know it's omega. Not in general, but just for y equals sine omega t. It satisfies this. Okay, now do it again. But we know this is 0. So what we have is we have s squared plus omega squared L y equals omega, or Ly equals omega over s squared plus omega squared. So if y satisfies this, then Ly satisfies this, then it's equivalent already to say that then this is going to be the Laplace transform of this particular y. So we got it. L sine omega t equals omega s squared plus omega squared. That will be the first Laplace transform for sine. This will be the Laplace transform of the first sine function. Okay, we didn't do the integration by parts for twice. We didn't find it from integral at all. We used the property of sine omega t to construct an initial value problem of second order, which we know sine omega t is going to be the answer. And then we find that if y is the answer, then Ly has to satisfy this. Therefore, this is going to be the Laplace transform of L sine omega y. Similarly, we can do the same thing for y equals cosine omega t. We construct the initial value problem that only this one satisfies, and then if we apply Laplace transform, that Ly, which satisfies the Laplace transform of the ODE, is going to be your Laplace transform. It's to come from here, for sure. Now, y0 is going to be cosine 0. That is going to be 1. Okay. Y prime 0, you can do it by yourself. Clearly, it's going to be 0. You can repeat the process we have. Okay, then we have s L y prime minus y prime 0, which is 0. Okay, and then s Ly minus y0, which is 1, plus omega square Ly equals 0. Therefore, we can finally have so Ly equals s over s squared plus omega square. That is going to be the second part. Of the formulas we need. So from here you can see it's very easy to memorize them because they share the same format, except one goes with omega, the other goes with s. And note, these two together will be the formula we need to memorize. And a note, even though they look symmetric, they're different because s is a variable. It's almost like x, and omega is a constant. So what you should really see is something like this. Okay, and L sine 4t is going to be s squared plus 16 over 4. So what you see here is variable and a constant. So they are slightly different, even though they look symmetric. But s and omega, technically one of them is actually the variable and the other one is a constant. So they are different. All right, with all that in mind, we have the Laplace transform of L sine omega t. Now we are ready to solve the first case, harmonic oscillator, or just say, yeah, let's do harmonic oscillator. No. Let's do the second order differential equation. Okay, the first one we want to do is undamped. Okay, so I have y prime prime plus 4y. There's no y prime term equals 0. All right, so what do you have? You do have harmonic oscillator. You do have L let's take 0 and 0. Okay, so solution L y prime prime plus 4 Ly equals 0. S L y prime minus y prime 0 plus 4 Ly equals 0. And S Ly minus y0 plus 4 Ly equals 0. Okay, this is 0. So s squared plus 4 Ly equals 0. Ly equals 0. This implies y equals 0. Now what do you have? You have a harmonic oscillator with initial displacement to be 0, initial velocity to be 0, therefore it's not going to be moving. Okay, for sure. So this is not too interesting. Now what we're going to do is we're going to give you a initial conditions 3. That means initially I have this one. This is relaxed, but now I pull it for 3 and no velocity, and then suddenly I release it. What's going to happen? So now let's change it. So what we're going to do is we're going to change this to 3. No, change this to 0. Change this to 3. Okay, then we can actually change the solution a little bit. This time we won't have 0 anymore. It's going to be s squared Ly minus 3s plus 4 Ly equals 0. Therefore, s squared plus 4 equals 3s. Ly equals 3s over s squared plus 4. Now, by the Laplace transform, we know this is going to be can take the 3 out because we just want a clean S. And because our inverse is linear, we can have this final answer by the Laplace transform. You can plug in 0, you got 3. Plug in y prime 0, you got, what do you have? You got 0, okay? And of course, it's a cosine 2t thing, so of course you satisfy the original thing. Good. So that's a Laplace transform thing. Assuming we already know the Laplace transform of cosine, we can recognize it. Let's make it a little bit more complicated. This time, we are going to give you an initial displacement. We are also going to give you an initial velocity. Okay, let's do 1 to separate them. Now what are you going to do? Okay, so SL y prime minus y prime 0. This is going to be 1. This is going to be 3. Okay, so minus 1 here. Okay. Then we finally have s squared ly plus 4 ly equals 1 plus 3s. S squared plus 4. Okay, 1 plus 3s. That will be the Laplace transform of our solution. So what is our solution? We just take L inverse. Now we have trouble, right? If it's just S, we have cosine. If it's just constant, we have sine, but we have both. So what do we need? We just simply split them. And this is going to give us the sine part. This is going to give us the cosine part. Now do them separately and be careful with the constant. Okay, first, for cosine, you need s squared plus omega squared. Therefore, you just put the sine in the front, a 3 in the front. For sine, you need omega s squared plus omega squared. Therefore, this one is going to be 2 over s squared plus 4. That is going to give you the sine. So you have to make a 2 here. Then just make a 1/2 in the outside to make sure you still have 1. So the final answer is going to be 1/2 sine 2t plus 3 cosine 2t. So when you have sine and cosine together, you are going to have a linear factor on the top. The good news is this part give you a sine, this part a cosine, this part give you a sine. So together you can always split them into a sine cosine, so it's always doable, as long as you match the coefficient. So not surprising or not surprising, partial fraction again. All right, so that's what we have from the undamped case. Number 2, the underdamped case. Okay, so we have y prime prime minus 4y plus 4y minus 4y plus 4y prime plus 3y equals 0. So now we are going to add in the friction. Okay, we know this is underdamped because we do s squared lambda squared plus 4 lambda plus 3. We know, okay, lambda equals -3, lambda equals -1. So our answer is going to be e to the -3t, e to the -t. So that's underdamped. We do not have cosine and sine. Let's make up some random examples. All right, so what do we have? Well, Laplace transform for the first round. From here, you can see actually from the Laplace transform side, there's nothing tricky. You just have one more term, and you know how to get rid of the y prime. So L S L y prime minus y prime 0 plus 4 Ly prime. So let's change it. SLy minus y0 plus 3Ly equals 0. You see y0, replace it by 4. You see this one, replace it by 1. Now a second. SLy minus y0 minus 1 plus 4 SLy minus 16 plus 3Ly. Okay, keep going. This is 1. This is 4. So finally, S square Ly minus 4s minus 1, 17, if you put 1 and 17 together, okay, plus 4s Ly plus 3Ly equals 0. Now let's clean everything a little bit. S squared plus 4s plus 3 Ly equals 0. Okay, so finally we have 4s minus 17. Okay. Well, the trouble is, again, this time, how to do the inverse Laplace transform. Well, what do you know? Partial fraction, right? What's going on here? To do partial fraction, you have to do the bottom first. Now you can split them. And then suddenly you realize, what is this? That's just going to be a constant times the inverse Laplace transform of 1 over s plus 1, which goes to e to the negative t, and 1 over s plus 3, which goes to e to the negative 3t. So we do have the two answers we had before. We expected. They're going to be underdamped. We have exponentials, right? So this is going to happen because we can do partial fractions. That is beautiful. The rest is just try to figure out what are the numbers. Okay, so quickly, as plus 3a plus bs plus b equals 4s plus 17. We have a plus b equals 4 and 3a plus b equals 17. I picked a really bad number. This implies a equals 13 over 2 and b equals, take the sum, 21 over 4. A plus b doesn't sound right. Hold up. Yeah, can't be. Okay, a equals 17 over 2, so this one equals negative 2 over 5. 39 minus 5, 34 divided by 2, that's 17. Okay, so we got this. So finally, L inverse we split them, so minus. So we can handle critical damped cases. The reason is because we can do the partial fraction, and the bottoms happen to be a multiplication of two linear cases. Okay, so we can split them, and linear case give you exponential. Only the quadratic, the irreducible quadratic, actually give you sine and cosine. All right, so from here you can see it's pretty easy to do things like that, at least for undamped and underdamped. If you take a look, okay, the first one, let me copy it. Y0 equals 3. Okay, then the answer we end up with is The second one is okay, and here our Ly okay. These are the things we have done so far. Okay. Now I want you to build one additional steps of connections. Can you write down the characteristics equations for finding the eigenvalue? We have done this before. That's just the same as this. We said, well, it's the same as, replace y prime by s square and things like that. The eigenvalue, the characteristic function of this one is going to be this. Now you need to ask yourself, do you see anything that's worth noticing? The same. The same. So how did you get actually lambda? You actually get it from this one. And then you get, okay, lambda equals -1 or lambda equals -3. But how did you get the e to the -2t and then negative t and -3t? You get it from here because you get s plus 1 and s plus 3. Therefore, they goes to inverse Laplace transform. Right? So actually what you got here is exactly the same as what we did before. And this is actually where everything we did before come from. That is, you look at the bottom, after you finish the second order derivative, you find your characteristic equation is actually at the bottom. It's the same thing. Is it true? Is it true in general? Okay, let's do it. Ly prime, so. Okay, these are constant, but what you should pay attention to is actually here. Okay. And here. Finally, y0. These are just constants, right? You can actually move everything else without a constant to the other side. And finally, put everything together. You have s squared plus ps plus q Ly equals y0 plus y prime 0 plus sy0. So your Ly is going to be a bunch of stuff which we don't care, but the one on the bottom is going to be this. So what do you have? Actually, the s square is produced when you actually take the Laplace transform for twice. Okay, for this term. The s term comes from Laplace transform for y prime because you have sly, right? And this one just have ly with no s. So actually, you are always going to get exactly the same characteristic equation at the bottom of your fraction after you take the Laplace transform. What you're trying to do is basically just try to transform everything before back into the original system. Okay, try to take the inverse Laplace transform of this. Okay, so what can happen? Well, what can happen is, number one, lambda squared plus, we have two distinct real. That's what can happen. To give you an example, then that means everything on the bottom is going to be s plus 1 and s plus 3, right? That's two distinct real. You are going to have two linear factors. And then you can further split them into s plus 1 plus s plus 3 with some partial fractions. And eventually that thing goes to e to the negative t and e to the negative 3t. Of course it's going to happen. Okay. Number two, what can you have? You have one repeated real. Two complex. Let's do two complex. So what are you going to get? You are going to get something on the bottom like this. This will give you either sine omega t or cosine omega t. This corresponds to s equals plus or minus omega I. So of course that gave you cosine omega t and sine omega t. And this case only works when your real part equals 0. What's missing? What's missing is what if my real part is not 0? That will give you something irreducible fact on the bottom, okay, as we will show later. And the last thing is going to be the critical damped. One repeated real. Okay, that is going to give you something we don't know yet, actually. We can think about it later, but I will show you right away. Okay, so but now we're going to follow this logic and try to keep going, but this time we are actively looking for that, how to do the partial fractions for different cases we just wrote down here. Two distinct real, which is already done. No doubt we got exponential. Two complex, at least for the undamped case, it's done. Now we just want to see the damped case. Okay, let's see the damped case. 4 Ly prime. Let's do minus. 5y equals 0. So y0 equals 0. Y prime 0 equals 1. Okay. Before we do anything, we're going to have something divided by s squared minus 4s plus 5. Okay, as we talked about before, this is going to be the characteristic equation on the bottom. So either way. Okay, I'm writing down all the details of this, so hopefully after we do it again and again, we finally start to get familiar with how to do Laplace transform. Minus y0. What did I do last time? I may have noticed. That is bad. Here's a p. So there's a p here. Yes, all right. Everything else will be okay. Now plus 5 Ly equals 0. So we have Ly minus y0. Y prime is 1, so minus 1. This is 0, so minus 4 Sly. This is 0. Okay, so together we have s squared minus 4s plus 5 equals. Oh, no, equals 1. Okay, and then Ly equals 1 over Okay, now we want to do partial fraction. How do we do it? Number one, we try to do the linear factor, but we know this is not doable because it's irreducible. Quadratic. Okay, then what we can do is we can complete the square and write everything into this. Okay, what do we wish? We wish this is going to be that. Then we know this one goes to sine omega t. Okay, but this one does not have it. What this one does have is it has a s minus 2 square. So everything here is you replace the s by s minus 2. Our next job is try to think about how do we do the inverse Laplace transform of this. It should be a modification of what's going to happen to sine omega t. So if I write it down, you should have something omega s squared plus omega. This gives you the Laplace transform of sine. Now what you want is actually omega plus omega squared, which is fine, but then your s is shifted a little bit. You want to know what happens to this. Right? But now, moreover, if you think about it, this is damped case. So just judging from here, we already know lambda equals 2 plus or minus I. The I part come from here. The 2 part come from here. And what does this do to our solution? This actually gives us a solution which does have sine omega t, but it also gives us a e to the 2t at the beginning. So what we're going to guess for this one here is this one somehow should be related to the e to the at sine cosine omega. Hopefully they're exactly the same, because what we got here is we're going to get s equals a plus or minus omega I. We do know what this a does to our solution. It add a term here. Okay, so that's everything we have so far. We have trouble. The trouble is we do have a sine, kind of like sine term, but it is shifted by a factor of 2, or in general shifted by a factor of a. And we're guessing it's associated to this one because we know everything about how to solve those kind of second order differential equations. So then, property or fact, whatever, we probably want to show if we add at here, we are going to take the sine omega t Laplace transform and shift s to s minus a. We want to show this. Okay, and it has to be true. Otherwise, either Laplace transform fail or everything we had done before about how to find a solution of underdamped harmonic oscillator, okay, is going to fail because they have to match, right? Speak of that, I noticed this should be overly damped, not underdamped. I remember I wrote underdamped. Okay, over. Right, so now it's underdamped. Okay, so can we show that? Well, let's try to see. Actually, yeah, let's just show. I don't remember if I showed this before. Did I show this before? Maybe I didn't. Okay, let's just show it for every single did I show it? I didn't show it. Okay. Let's just show this one works for every function. If this is true, then you just take the f to be sine omega t. Of course, this one is going to give you the shifted thing. All right. Okay. And meanwhile, we can actually get this part for free. Once we can show this, we can also get this one for free. Okay. Once we can show this, we can also get the other one for free. Without e to the at, it's this. With e to the at, as we are going to show later, you are going to shift everything to change s to be s minus a. So this is going to happen. These are the two things we need to know. But now I want to show they actually come from a fact that is what we're going to try to show. All right. So it's actually pretty straightforward to write down everything we know. That's the Laplace transform of the left-hand side. Okay, now you can easily see, where is it? Oh, yes, here. Okay. So this is basically this. Okay, but replace the s by s minus a. Therefore, this is going to be the Laplace transform. Just replace your f's to be s minus a. So this is certainly going to be good. Then we have this thing here. All right. So this is basically coming from omega s squared plus omega, but to replace s by s minus a. This comes from s over s squared plus omega squared, to replace s by s minus a. We have these two. So once we have that, let's continue with what we have here. We started from this. We end up with we try to split them into two linear factors. We find these are irreducible. Therefore, there is no way we can change it to be exponential, but instead we can do this. Now you can get it from this. You can see it's nothing but this one changed s to s minus 2. Therefore, the whole thing is going to be sine omega t, 1t. But shifted by 2, so you multiply by e to the 2t. That would be the answer to this initial value problem after we do Laplace transform. Of course, we need to use a little bit modified of the Laplace transform of sine omega t. And all we did was replace s to be s minus a. And that effect on your solution is going to be you are going to multiply a e to the at on there. So the real part, the imaginary part, matches perfectly with what we have talked about before. That is beautiful. Okay, so we have another way to do partial fractions. Before we can do linear, we can do irreducible quadratic when you have undamped case, but now we can do underdamped case, where your real part is not necessarily 0, but all you do is just multiply e to the at, which is exactly what we got from eigenvalue and eigenvectors. Okay, so the final case, we want to talk a little bit, that is going to be critical damped. What will happen to this? Okay, y 0 equals 0, y prime 0 equals 1. What is going to happen to this? Well, old knowledge, lambda squared minus 4 lambda plus 4 equals 0. Okay, lambda minus 2 square equals 0. That's why I have repeated real. Okay, that will corresponding to e to the 2t plus t e to the 2t with the v0 and v1. Remember what we did before? Okay, eigenvectors and with lambda I minus a minus lambda I, solve v0, whatever, the whole bunch of stuff. But now we are supposed to get the same thing, this time from Laplace transform. So the first step is try to do this. Prime 0 minus 4 ly prime, so you can do it. Plus 4 ly equals 0. So y0 is 0. This is 1. So we have s ly minus y0 minus y prime 0, which is 1, minus 4s ly plus 4 ly equals 0, which is s squared minus 4s plus 4 ly equals sy0. y0 is 0, so then what do we have? We have s. That's it. All right. So our job no. Our job is try to do the inverse Laplace transform. That's it. Okay. So how do we do this? I still don't feel right. Do I feel right? Y prime. Yeah, that's why I feel weird. Keep doing this. Okay, this is going to be a 1. Okay, so now we are going to try to do the inverse Laplace transform. No, hold on. This is 1. The next step is this. After I divide. So number 1, no surprise, we do have the original characteristic equation on the bottom. Okay, now we can see what's going on. If this one has 2 distinct real, we can split them. We're going to have an exponential and exponential. Good. If it's irreducible, then we can have the complex eigenvalue. Of course, we have 2 solutions. We just wonder, okay, after we complete the square, do we have something like that? Because if you have that, we multiply e to the at. Otherwise, it's just purely sine and cosine. So that's okay. This one is different from either. The reason is because the bottom is going to be a factor of 2, a multiplication of 2, but these 2 factors are the same. Therefore, you end up with something like this. It doesn't make sense to split this one into 1 over s minus 2 plus another number times s minus 2 because they gave you the same solution, right? So we need to actually go directly from here. That's why it is complicated. Okay. If you think about partial fractions, this actually is what we had in calculus 2. That is called the repeated linear factor, which cannot be handled as a linear factor or irreducible. It's slightly different. Well, so what do we know? Well, let's think about it. We do know this. Okay, that's the Laplace transform of e to the e to t. All right. What's the relation between these two? And hopefully that will give us some hint to what will be happening on the other side. Well, number 1, this one is actually this one squared, but that's, you do not carry those kind of things, right? So you cannot just do this. Some operations can be carried away even if you apply a L, which means it's exchangeable with the integral sign. And then if you take a closer look, maybe spend several attempts, you can realize this is actually the derivative of this with respect to s. Okay. Now, what's going to happen if you take the derivative on this side? That means you have to take the derivative on the other side, right? Because L e to the 2t equals 1 over s minus 2. And if you want to get 1 over s minus 2 squared, you have to take the derivative with respect to this. Okay. Then you have to take the derivative with respect to this on both sides in order for them to be the same. Now the question is, how will this one change the function inside? That's what you want, okay? Which we will try to do right away. But now what do you think will happen? That is definitely going to give us this, because we know it is a solution, right? So now we just need to try to see, with that hint, can we actually get this? Well, let's take a look. What's this? The right-hand side is easy, so let's do the left-hand side. Okay, and let's take it already. Now I want to take the derivative with respect to s of the whole thing here. Where's s? this one. So I can treat everything else as a constant, even within the integral sign. So I can take this one in. Because this is the only part that has s in it. Everything else has no s, right? So we can treat them as constants. Now, what is the derivative of this? That is going to be, if I'm taking the derivative with respect to s, t is a constant. All right, now let's clean things a little bit. I want to take this t and put it together with this one. All right. I want to put the negative sign in the front. I want to keep this one here. Now, negative, negative cancel. All right. This part, as well as this part, is nothing but the definition of the Laplace transform. So this is going to be this. Which means and that's exactly how we got the solution from here. We do have a t times e to the negative 2t. Before we kind of guessed what's going to happen. We said, well, this one will make sure that the original thing can be satisfied because it doesn't create additional terms other than itself and the one we already have, which is e to the 2t, when we take the derivative. But now we have a solid proof, that is Laplace transform of that thing is going to be this. Okay, so how did we get it? We end up with, for critical damped, we end up with something with a repeated linear factor. The good news is this one always comes from the derivative of this. Just take it for once, you got this one squared with a negative. Now, if you can take the derivative with respect to s to get this one, you can take the derivative with respect to s in the original Laplace transform. And then we figured out, actually, you can just put that thing in, do some simplifications, you figured out a nice property, that is, this one will give you this. Then if you do the inverse, that will be your solution before you take the Laplace transform. All right, so that's everything we have done so far. It's beautiful. They're connected. So let's try to write down what we have done so far. Number one, we have two distinct real. And we realize, okay, when we have two distinct real, that basically means, okay, we can actually do this. Okay. That will give us lambda to the negative at. Let's use minus to make it. That's what I get from eigenvalue and eigenvectors, right? Now what do we have if we just do it in Laplace transform? We're going to have Ly equals the same characteristic equation, but you change lambda to be s. Then we are going to split them into, so of course your final answer is going to be C1 plus C2 EAT because of the inverse Laplace transform and EBT from the inverse Laplace transform of that part. Great. What about 2 complex? That means when you do this, you have lambda squared plus p lambda plus q lambda, a q equals 0. And somehow you did it. You can actually do lambda plus a square equal plus b square equals 0. Okay, that will give you lambda plus a square equals so lambda plus a equals plus or minus b I, which give you lambda equals negative a plus minus bi. Okay. So this is going to give you a solution e to the negative at cosine bt and e to the negative at sine bt. That's what we got from the original thing. Now, you got exactly the same thing with Laplace transform. You have Ly equals something. But again, let's change to S. Okay? And we compare them to this give you sine. This give you cosine. Now what you did is just you simply shifted everything. So you have sine bt, you have cosine bt, and then change the s plus a, simply just you shift everything by times e to the negative at. Okay. So two ways of understanding the same thing. One from the original eigenvalues and the other one coming from the Laplace transform and the property of Laplace transform when you multiply with e to the at. That is great. And finally, number 3. What you're going to get is lambda plus a square equals 0. So you have lambda equals negative a repeated. Okay, then lambda equals negative a for twice. You are going to have e to the negative at and the e to the negative at. Okay, what about Laplace transform? Then you are going to get Ly equals lambda plus a s plus a square. And you can split it into a over s plus a plus b over s plus a square. This is exactly what we get from what? From partial fractions, right? So the first part, if you do the inverse, it gives you this for no problem. The second part, if you do the inverse, it gives you this. And we did a whole bunch of things by taking the derivative of this one with respect to s. Okay, so that is beautiful. Everything is beautifully connected from different perspective though. So from now on, every time you do eigenvalue and eigenvectors, you can connect them with partial fractions. How many cases do you have here? Totally depends on how many partial fraction cases you have from here. Okay, all the techniques are exactly equivalent. It's just a matter of which way you want to do it. Okay, that is beautiful. Okay, so if I were you, I would take some time and reflect what we had in chapter 3, and then try to match them one by one. Okay, you can even think about what will happen to lambda equal to 0. Okay, so that would be corresponding to lambda times lambda plus 2 equals 0. You have two eigenvalues. Negative 2. So how are you going to write down the solution? Okay, and then compare it with the Laplace transform. What you're going to do is you're going to split them into this. Okay, so one part give you e to the negative 2t, the other part give you a constant. Because we know the Laplace transform of 1 is 1 over s. So it's going to be a constant. So all the cases we had before will be covered. And they have exactly one-to-one corresponds, but you have two different ways to understand what's going on. Okay, that is very good. Especially you start to see the good thing about Laplace transform. That is, everything from involving derivative will be transformed into algebra. It's purely just multiplication, dividing, all the stuff we have done before in college algebra. You don't have to think in terms of like changing rate or integration even though that thing is actually hidden in the operator of Laplace transform. Okay, that's a lot of examples. Okay. Finally, we want to handle the last case, which we haven't done before. That is number 3, forced harmonic oscillator. Oscillator. Okay, so let's solve 2 examples. The first example is going to be, like we said, you may have something shaking, oscillating as before, but now you make it charged and then you apply like an electrical field, which is oscillating, alternating, okay, with a different frequency. Now let's try to solve this one. Before, this is not something we can do. We always solve homogeneous case because we want the linear properties, right? We want to be able to write down C1y1 plus C2y2. And you can easily verify this time C1y1 plus C2y2 won't work. Okay. But now with Laplace transform, we can do it. Actually, you can do it as long as you know how to do the Laplace transform of the right-hand side. So far, we can do exponential, we can do sine, cosine, and we can do the delay heavy side function. Okay. This is gone. This is gone. So finally, it equals S. There is a S. Oh, this is bad. See if I can make it up. Yeah, looks nice. Plus 4. Ly equals to the right-hand side, and for the right-hand side, we know it's going to be s squared plus 3 squared, which is 9. Okay, so what is your Ly? Your Ly is going to be s over s squared plus 9, s squared plus 4. This comes from the external force. This comes from the original natural frequency, which we get from the Laplace transform or characteristic equation. Okay, it's just a matter of how do you make this happen? Well, we can do partial fractions. We use A, B, C, D. A, S plus B, C, X plus D. Okay, so we have A, S plus B, S squared plus 4, plus CX plus D, S squared plus 9. Somehow, if we pick the constants A, B, C, D, we should get S. That's the on the top. Okay, so what we are going to have is AS cubed plus BS squared plus 4AS plus 4B plus S plus D. CS cubed plus DS squared plus 9CS plus 9D equals S. Now let's do the S cubed part. It's going to be A plus C S cubed equals 0. Now X as a square term. B plus D S squared equals 0. The S term, 4A plus 9CS equals 1. Finally, 4B plus 9D. And we don't have a constant term on the right-hand side, so this is 0. Yes, okay. Now what do we have? Let's solve it. Let's look at number 1 and number 3. We have A plus C equals 0. We have 4A plus 9C equals 1. Therefore, if you A equals 1/4, 1/5. Something is wrong. Actually, that thing is wrong. I copied the wrong thing. So the one in my notes is 3 cosine t. Okay, so the answer I am getting here is not going to be matching what I have in my notes, but it's fine. So maybe there may be some mistake here. I maybe have done some algebraic mistake. Okay, but the idea, I think you can get it, and you can eventually modify it by yourself if necessary, because I copied the wrong problem. But since we have done something so far, let's just finish it. Okay, so that's the first part. Good news is it's still nice. Now the second part is b plus d equals 0, and 4b plus 9d also equals 0. So I think b and d are 0. It's fair. So now what we have is, we are going to have, where is it? Here. Okay, so a and c, so L y equals a nine. Four. Okay. Assuming my algebra is working, this will be the same we got after we got a, b, c, and d. Okay, got b and d are 0, so we only have the s term. Now y is going to be that would be the final answer. Okay, I think it's working. Plugging y 0, it's 0, and plugging y prime 0, it's also 0. Okay. All right, so what do we have here? We have something very interesting. You know, we have a wave, a superposition of two waves. Okay, one of the wave is cosine 3t. Where does it come from? It comes from the external force. Okay, now where does the cosine 2t come from? It comes from the natural frequency. Okay, so this is actually external. This is natural. So if you have a spring oscillating at a certain frequency, and then you have external force also oscillating at a different frequency, then eventually your final motion is going to be a combination of both. It's a superposition of the natural frequency plus the external frequency, which is fine. You can also give it a constant force and try to see what's going on. You can also give it an exponential force, growing or decaying, to see what's going on. So that is totally doable. And from here you can see there's nothing difficult in doing everything with external force using Laplace transform, because as long as you know how to do the Laplace transform, as long as you know how to do the partial fraction, you are all covered. All right, so finally, the resonance. I think everybody who has done this before, to realize this, the next thing in your mind is actually, I want to try this. That is, what if I have something shaking at a frequency, and then I try to add another external force with exactly the same frequency? Okay, that is, if I have a y prime prime plus 4y, which is already a natural frequency with 2. Then I induce it with another, let's just do cosine. With another wave, but this time with the same frequency. What am I going to get? Okay, well, let's try to see. Initial value. Actually, let's just let y0 equals 0 and y prime 0 equals 0 for simplification. Other cases we can do it, it's just going to give you a very complicated partial fraction. So let's just focus on this. Okay, so what's going on? You have something which is not shaking at all, and now you give it actually an external force and try to see what's going to happen for this. Okay, now what's going to happen is, on the left hand side you will have this, all the constants are 0. On the right hand side you are going to have this. So finally your Ly is going to be S s squared plus 4 times s squared plus 4. If these two numbers are different as before, you are going to further split them into s squared plus 4 and s squared plus 9. That's how we did it last time. We are going to use partial fractions. But this time, again, we have a case which we cannot handle by splitting them because we have repeated. That's the problem with resonance. That is, you do not split them into two waves. Actually, the two waves merge into one term, but repeat it for twice. So you cannot simply just split them and get two waves with different frequency. You get something like this. All right, so now it's the problem. How do you do this? Okay. Then again, we are familiar with this. Remember what we did was like something like that. We say, well, we don't know this, but we do know this. And somehow if we take the derivative, we get this. For the same thing here, it's repeated. It's hard. I'm more familiar with the unrepeated. That is 1 over s squared plus 4. That gives me sine 2t. And what's the relationship between this and that? Well, since we have already done it, maybe let's just take the derivative. What's the derivative of this? Number negative square 2s. Similar? Very similar. Okay, then I think we can actually go ahead. I think you already know what I'm pointing at. So you have L sine 2t equals. Now we want to generate the term we want by taking the derivative. I didn't write it down as a general principle, but you can actually summarize it. What you're going to get is t times sine 2t. You just add another t every time you take a derivative with respect to s. But since we're not focusing too hard on that, let's just redo the process. And you can see, okay, every time you take the ds, you're going to have this, and you're going to generate a negative t. Okay, and that can be merged into negative 0 to infinity t sine 2t. Then you see, well, that's the Laplace transform of this one alone. Okay. T sine t. Okay. And this equals the derivative of that. The derivative of that is going to be square negative times the derivative of the inside s squared plus 4, so times 2s. Okay, so it's settled. L t sine 2t equals 2s s squared plus 4 square. Now what do we got? We got Ly this is what we got from the differential equation. So the solution of this is going to be when you have something like that. Let's just say okay, so put an external force which matches the natural frequency is going to give you a solution which is not sine and cosine anymore. It's going to be t times sine 2t. We call this effect resonance. Okay, so what's happening? if you have a superposition of two waves, one wave is like that, one wave is like that, you just sum them together, that's fine. Okay. But now what you have is sine t. But then the amplitude of sine t is going to be t, which means as time goes by, the amplitude become bigger. So you are going to have something like this. Same frequency, but keeps amplified as you move on. So yeah, forget about how I draw it. It's just going to be something shaking, and as time goes by, it just, vibrate more and more severely. That's what's scary in real life. That is what we have for resonance. The sound barriers, the shake of the bridge when you have an earthquake, when you have people even walking on it, when the frequency matches, and also when you receive signals from a radio, we're all exploiting the effect of resonance. Okay, so some examples like sound barrier. When you try to build a supersonic airplanes, this is going to be something you will be worried about. Okay, you have earthquake, which actually induce a vibration on bridge, which you can Google online and just search resonance bridge. You will see some very scary videos from YouTube to show you how the bridge basically shakes like a spring, or it shakes like a rope. It doesn't look like concrete at all. And then, of course, something like radio, where you use resonance to actually, receive certain signals for certain frequency. All right, so that's the resonance effect. From here, you can see, well, we are going to have repeated irreducible quadratic case, which is another case of partial fractions. From everything we have done so far, seems like we can handle it as long as we know how to do, number one, partial fractions, and number two, how to do inverse Laplace transform. That will be all the cases for second order.